So the first speaker in this afternoon's session is Lou Gritzo. Lou is Vice President and Manager of Research with FM Global. And I'll let Lou explain who that is. If you don't know, I suspect that you do, but if you don't, I suspect you'll explain it. And it's quite important for us to have invited FM Global. FM has been a supporter of research at Edinburgh, predominantly under the reign of Torero, but long may it continue. In any case, whenever you're ready.
Thank you very much. It's certainly a pleasure to be here. I'm going to start off by saying there will be no equations in my talk. When the challenge with Dr. DeRis, I'm not going to try and follow that. Also, just for a word of view, if you don't know who FM Global is, and I talked to a couple people over lunch, we're basically a commercial industrial insurance company. We're owned by our clients, so we're still one of the old mutual insurance companies. But we're really an engineering company that writes insurance. So we have 1,800 engineers, 1,300 engineers in the field, and no actuaries. And the way this works is our engineers go to a client's facility. They do a risk assessment according to standards that we develop and we write for property loss prevention that include all risks: fire, natural hazards, explosions, anything bad that can happen to a commercial industrial property. And they provide that client with a risk assessment. And we underwrite, in other words, we provide an insurance product, how much coverage, deductibles, rates, based on that engineering risk assessment. Okay, so there's no actuaries looking down a table and coming up with a rate. We basically underwrite based on that. And the reason is that we want to work with our clients to drive their risk down. And by working with our clients, the recommendations that we provide them through that risk assessment to drive their risk down, they benefit, we benefit. It's a win-win situation. Okay, so that's our whole goal. The end purpose of me talking about our fire modeling strategy is to provide those standards the very best information possible so that our engineers can work with our clients to drive their risk down, so our clients have fewer losses and we have fewer losses. Clients own the company, so it's mutual benefit. And it works. Our combined ratio last year, which is our profitability, was 77%, which means we only paid out 77% of what we brought in. This year we're giving back $465 million to our clients in terms of a membership credit as part of their ownership. So it does work. I'm not going to try and go through an exhaustive review of CFD fire modeling. Instead, I'm just going to mention that about 40 years ago today, a set of experiments were done called the Harvard home fire experiments. They were kind of the basis for the first kind of zone model that was well known, called the Harvard zone model. And so what I'm going to do is talk about where we are as a company from then. So at that time, this is what our research facility looked like, the FM Global Test Center out in the woods of Rhode Island. This is what it looks like now. It's a little bigger, a lot busier. And really the reason for that expansion is that fire protection today, whether it's in our standards or any other standard, is still largely based on full-scale tests. Okay. That's the way it is. You want to set a fire protection standard, you have to set it up and build it and burn it and show that it works. So here's the challenge. The challenge is for taking a simple thing like warehouse storage. If you look at all the variables that are involved, the different ceiling heights, different materials that are stored, the different aisle widths, how those things can be configured differently, and I take my most productive year at this facility where we did 300 tests, large-scale fire tests in 1 year, and I look at all the variables in this problem, it's going to take me 35 years to do all those tests. Okay? If I do one for every possible combination. Okay? So that's not sustainable, right? So the way we do it now is we test what we can, we use judgment, we try and fill in the blanks, but the challenge is that industry's moving forward a lot faster than that. New things are being stored in new ways, in new buildings with lighter construction, more plastic, and we've got to stay on top of that problem. Okay, so that's really our motivation for doing fire modeling. And the work you're going to see here is not mine. If I use the restaurant analogy, which I've used in the past, you're not getting the master chef talking to you about the meal. The master chefs are all at another meeting in Norwood, Massachusetts. You're getting the guy that printed the menu. Okay? All right, so that's the message. I'm presenting the work of a lot of other people. I won't be able to acknowledge them all along the way, so just go into that with that understanding. Right? So the goal is to perform better tests. The first thing we did 9 years ago when we were looking at this problem was improve our experimental test quality. We're the only large-scale test facility that controls moisture content of the material very tightly. Makes a big difference. We made a lot of improvements in terms of our test quality. The goal now is to be able to do fewer tests and do them smarter, and of course, provide deeper knowledge, engage and advance the community. About 9 years ago, I did kind of a survey of all of our academic partners. Edinburgh was one of them. And I really took a message home from Edinburgh that stuck, which is I heard from Jose and his colleagues that, what they really need is a platform on which to do fundamental research where they can publish their results in high-quality journals. Okay. So I compare and contrast that with what John said this morning, which is, there's hundreds and hundreds of tests and correlations on a certain problem, but there's not a lot of knowledge on it. So we need to move beyond that. We need to engage and advance the community to improve the rigor and fidelity and the trajectory of making advances in fire science. So that's part of the underlying driver for what we're doing here and kind of our strategy. And then ultimately to provide better protection. And better in this case means not only does it work, but the big issue for any kind of fire protection or any kind of fire safety issue is cost. Very rarely are you going to improve a commercial industrial property owner's profitability by a better protection system in the short run. In the long run, absolutely you will. Okay? Not only will they have fewer losses, they don't have the deductibles to pay, they don't have their insurance issues to deal with, they don't lose market share, they don't lose shareholder value, they don't lose employees, they don't end up in the nightly news, all those things that go along with reducing losses. Those are long-term benefits. The short-term challenge is how do you provide that protection cost effectively? Okay, so hopefully I set the stage for the fire modeling program we put in place in 2008. We made investments in staff and scientific computing. Our board of directors approved it. Our fire modeling objective was to reduce the number of large-scale tests needed to protect some simple storage. Basically what we call Class 2 commodity, which is a metal box with 3 to 6 layers of corrugated container board around it. Corrugated container board is a nice way of saying cardboard. So it represents an appliance being shipped or stored in a warehouse. Then down the road, we want to be able to have some predictive modeling capabilities for some applications. Okay? Not everything, but for some. So at the time, we looked at the challenge and the team that was responsible for this. Obviously, it's multi-physics, multi-scale. I don't need to go through that for this audience. But the basics is we need to calculate the fire growth and we need to calculate the efficacy of different protection strategies. Okay? And we started by just tackling the simple warehouse problem, right? Just because of the magnitude that I talked about. Now, it's not like we're burning down warehouses every day, thankfully not. Part of the reason for attacking that problem is pretty well defined in scope. It has a lot of the features of key geometry. There's a lot of business value in warehouses. When a company loses their warehouse, they have to overcome that. We have a lot of things that we ask our clients to do to protect their storage and warehouse that's a hassle for them. So if we can alleviate some of those issues, then we're ahead of that. And it's also just a good canonical problem to start with. A little simpler. So that's where I'm going to start. Warehouse is not the end goal, but that's certainly our starting place. So at the time, we used FDS. We used commercial codes, a number of different commercial codes. So we had a first strategic decision to make. Were we, as accomplishing those goals, going to try and build upon those, or are we going to do something different? And this was a big driver. If you look at computing performance, I think you've probably all heard of Moore's Law, it's really played out. You can do now on your laptop what used to take a supercomputer to do. It's not slowing down. So the machine that we bought, the first Linux cluster that we bought in 2008 was a little over a teraflop. Okay? Just 5 years before that, that would have been one of the 500 fastest computers, which is shown on the orange line here. The fastest computer is shown on the red line. Okay, so you can see how both the fastest computers in the world and the top 500 computers and notebooks and everything else are going along this linearly increasing scale with time. Okay, so we didn't want to build something for today, we wanted to build something for the future. So computing was not the big issue for us. We're not going to build something that runs on a laptop. Okay? What we're going to do is take a strategy that says, you, the students that are out there, are going to have computing resources that far exceed anything we've ever had, and we don't anticipate that's going to slow down. So we're not going to limit our strategy to a laptop, and I'd suggest that the discussions moving forward not be limited to that context. We need to think beyond that. This is the trajectory we're on, and it's showing no signs of slowing down. So the other key factors is complexity. Obviously, we want to move beyond warehouses. Even a warehouse, I mean, warehouses are tens or even hundreds of thousands of square meters. So we need to represent that size. And obviously, the rigor from a scientific perspective, all the physics that we need to capture require a higher fidelity model. So we chose to start with an open foam toolbox. This was developed by Imperial College. It's supported by OpenCFD. It's something which is available through OpenCFD. Our strategy was to develop the key models and call it FireFoam. I wanted to call it OpenFire, but people thought that sounded bad, so we ended up calling it FireFoam. But only to develop the key submodels that are needed to build upon that platform, which has a very good solver, a set of solvers, a maintenance program, availability, to be able to do what we thought would accomplish those objectives. Okay? Better protection, move the community forward, and be able to solve the kinds of problems that we need to solve in the future. It also gives some acceptance, and it helped our cooperation with academia and industry. Okay? We didn't have any licensing agreements. We have this model available. If you go to fmglobal.com/modeling, anybody can download it. Our folks here at Edinburgh can develop submodels for it, as they have in the past. So that was our strategy in terms of moving forward with making a selection for a fire model. We have annual workshops. The unfortunate part, maybe the reason I'm here today, so fortunate for me, is that this year, this meeting and that workshop were announced on the same day as being on the same day. So all of the folks that do the heavy lifting are at this workshop, and I'm not expecting you to see the agenda here instead of here. So I get a chance to come here and hang out with you and have a nice dinner and learn a lot. But this is where the folks are at this workshop. And that's where the knowledge is shared between the community that's working on it, moving this model forward. The rest of this I'm going to go through pretty quick. It's a CFD model. I think most of you know the equations are solved on grids and time steps. We use separate grids for the solid, gas, and the liquid. The spray droplets are modeled in the Lagrangian transport. Right now, for a warehouse calculation, it takes on the order of days to run. We have about 12 teraflop machine. But the nice thing is you can run 4 or 5 scenarios at one time. In a few days, you get an ensemble of results, and you can use those results to make decisions. Our milestones are as follows. We started with the buoyant plume. Then we used the 8-foot parallel panel test in 2009. Then we used a simplified 2x4x3 rack storage, free burn in 2010. Then some free burn with water application at prescribed rate on the top, and then the rack storage sprinkler protection. And I'm going to walk you through these right quick, kind of how we did along each step. We use a pyrolysis model that's built on the FPA. Basically fuel properties from bench scale. We have a material decomposition modeling approach that was developed in part here at Edinburgh. And then the validation is for fire growth is in the parallel panel and in the rack storage case. So this is an opportunity for those of you that are developing models to develop them in a way that will allow them to be used by others. Okay? So developing pyrolysis models in some standard way helps those models to be used by others for calculations using the same material. The parallel panel test is an important one for us. This really captures one of the things that Patrick was mentioning. This is the way we started testing and certifying wall panels. We used to use a big corner test, 25, 50-foot corner test. We don't do that except for in very rare cases. This is either an 8-foot or a 16-foot, 2 panels put together facing each other, which replicates the radiative environment of a corner. And you can put the seam of a sandwich panel right in the center. Okay? So you can capture those kinds of things. It's easy to capture in terms of the boundary conditions are it's a simple geometry, well-controlled boundary conditions, good kind of canonical problem, and you can see how we started off just modeling flame spread through parallel, clean geometries. Our next step then was to be able to do rack storage. So we developed the basic pyrolysis model for corrugated container board, then we applied it in a more complex scenario. You can see the tests, there's 2 different configurations. Tests on the right, model on the left. I mean, the first thing is the view graph test, right? The first is view graph validation. If it doesn't validate on view graphs, it's not going to validate in numbers. So this is necessary but not sufficient for validation. You can see the flame spread rates are about right. The propagation of flame through the material is about right. This is what we call simplified class 2. It's basically boxes that are sitting on single points, so we don't have the complication of the heat sink back into the rack. I'll talk about where we've gone beyond that here in just a minute. But You see that the basic flame structure is okay. What we're rendering on the left-hand side is the envelope of the mixture fraction space needed for combustion. So get some fairly good view graph norm comparison. And the heat release rate, at least the fire growth rate, is pretty good. Now, later on in the fire, when you start to get a lot of geometric changes, the comparison breaks down. But for us, in terms of looking at effective protection, the most important part is that initial growth phase. That's the key part to capture, because that's going to determine when sprinklers activate and how effective they're going to be. So the next step is, let's just use sprinklers protection as the first metric. It's still the most widely used protection mechanism specifically for warehouses. So the idea is to look at the sprinkler discharge, look at the discharge of those droplets through a flame zone, and then look at the transport of that water on some burning material. So it's the three basic steps required. We used a technique we worked with the University of Maryland to characterize selected sprinklers, basically getting the flux, the droplet size, and the number density with a combination of collector pans and laser diagnostics. And that allows us to track the droplets through the domain. So we don't try and go up to the sprinkler itself. We draw a boundary around it that's on the order of 0.5 meter in hemisphere, and then we specify the flux and those parameters at that level, and then track the droplets in a Lagrangian particle tracking technique through the space. So you have a K14 and you have it at some pressure. You set it up, you make this measurement, that is what goes in your model. The first validation was, can we do the actual delivered density correct? This is the density that gets through the flame zone to the top of the burning material. You can see the comparison here of experiments and measurements. That's basically tracking the Lagrangian particle tracking algorithm, the evaporation algorithm. The hardest part of this, and we knew this to begin with, was going to be what happens when the droplet hits the material. What do you do then? There's a fair amount of different options there, a fair amount of physics there. None of them are necessarily new physics, and I think this is characteristic of fire protection engineering in general. There's not a whole lot of new physics. It's just a combination of physics and the complexity that makes it challenging. So we looked at partial wetting and the heat transfer from that with a thin film model, and then couple that with the gas phase and solid fuel models to see what happens after a droplet hits the surface, partially wets the surface, then where does it go next? And there's kind of three basic cases. There's the thin film flow, which is a Nusselt solution, the partial wetting, which happens when that liquid starts to evaporate, surface tension pulls it together in rivulets, and then there's the transport from tier to tier. So if I have water flowing down the face of a box, what happens when it gets to the bottom? Some of those droplets, by surface tension, attract and go along the bottom. Some of them go some distance and fall down. Some of them drip down. Some of that water just washes down. So here's the combination of the models that were put together by Carl Meredith. He's actually our technical team leader for the fire modeling. He has reports to a group manager, Yi Wang, and Sergei Dorofeev is the area director for this area. So you can see the droplets, and this is a prescribed flux of droplets hitting the depth of the water layers represented by the tones here. You can see the pooling on top, the transport over the corners, the rivulet flow down the side, and the dripping off the corner. Okay. And so we validated this for a number of steps through some intermediate scale experiments, as well as some kind of combined experiments. And just like the home fire project back 40 years ago, where they did experiments for discovery, then they developed a model, and then they did more experiments to compare the model. Basically the same approach for all these. We use three different meshes. We have a mesh for the solid that does the heat transfer, a mesh for the liquid that does the thin film transport, and then, of course, the gas mesh for the fire itself. So here's when we put it all together for a simple material. Here's what it looks like. We have two different sprinklers in this case. We use a sprinkler activation model, which is a simple heat transfer model. You can see the little dots up on the left in the model. Those are our sprinklers installed in the ceiling. We just calculate the convective flow and use the response time index to trigger when those sprinklers are going to open. So it's very similar to the fire growth case you saw before, but now you're going to see sprinkler activation. And for a couple different sprinklers running at different pressures, and the transport of the droplets and the effectiveness of those droplets in terms of achieving fire suppression. So it takes a few minutes to develop. You can see that a sprinkler at the top, which is a K14 ESFR, it's an early suppression fast response pendant sprinkler. You can see the droplets. That windowing or the striping is a rendering of is a consequence of the rendering. That's not a calculated feature. You can see it's like pulsing. The spray looks like it's pulsing. You see the transport down the boxes, the rivulet formulation, and you can see it, really in both cases. You can see, the test is a little harder to see because the rivulets are a little more difficult to see with the glare from the light. Subsequent activation then has not occurred. Actually, you can see that 1 K14 ESFR is controlling the fire quite well in the top. But you will see subsequent activation on the bottom, which is the K11 ELO running at a little higher pressure. The one thing we haven't tackled here is sprinkler skipping. The advection of the droplets from one sprinkler to another sprinkler and wetting that sprinkler link. We haven't tackled that problem yet. That's something we need to tackle, or the community needs to tackle, because what it does is drive up protection requirements. When you put a safety margin in to account for the fact that those sprinklers are going to skip, it drives up protection requirements. So you see additional activation down below. And we basically compare heat release rate, sprinkler activation rates from tested experiments as kind of the ultimate validation, numerical validation. Of course, the first thing is, do you get suppression in one case and not suppression in the other? Okay, so this is the strategy that we've taken to start to do some test planning now. When we're looking at these materials, we'll run pre-test calculations. I don't know if you're familiar with statistical design of experiments, but we also use that as well to map out the test matrix. Our cooperation, again, all our folks that were involved in this are just too many to mention, but these are the folks that have traditionally been involved in the workshop. There's the 4th workshop in 2012, the 5th workshop, we're on the 6th one this year. So in terms of looking forward, what are we doing now? What are the opportunities for this group, and how can we best work together? We've completed that 5-year plan. We have the ability to model fire and suppression in those simple kind of warehouse configurations, reduce our test burden there. We're going to split our next 5 years based on applications, which I'll show you a few of, enhancing current models, which are research opportunities, and then new model development, new physics that we need to put in the model, pieces that are not there. One of the challenges that we face now, and I say we as a community face, is the notion that space is important, and when space footprint gets important, what happens? People build up. So we now have materials that are stored in 60, 80, 100-foot tall warehouses, whereas 5-10 years ago that never would have happened. Our research campus, which I think there's one actually at TFRI that goes a little bit higher, which is the tallest large-scale test facility that's regularly operating, goes to 60 feet. And so we're going to need to extrapolate protection to those levels, specifically in things like roll paper, where you can't mount them in racks and put in-rack sprinkler protection on it. In-rack sprinkler protection is the second option for warehouse storage, but nobody likes it except for sprinkler manufacturers. They sell more sprinklers that way, but clients don't like it, warehouses don't like it because they get hit with forklifts. There's all kinds of issues associated with them getting broken off. There are additional expense, both in terms of installation and maintaining the water supply. So design of in-rack sprinklers, testing of roll paper, which the roll paper properties were developed using the same approach, is some of the things that we're working on now that then will go into protection measures for those applications. We'll do design of experiments, we'll do limited tests, do the validation, and they go into protection in our standards. One of the things that we just recently achieved, which I skipped over a minute ago, was we did this year add the effect of wood pallets underneath the material. And it's kind of interesting. You take a look at the plot, and the red line is the fire growth rate with a wood pallet. It turns out if you just put the bare box without wood underneath it, that corrugated container board, that cardboard, ignites very quickly and produces a lot of flame spread across the bottom. The wood pallet initially lowers the fire growth rate. Now, of course, later when that wood gets involved, you see the heat release rate go up. But that's something that I think at first the folks that were plotting the data thought maybe they'd made a mistake. A higher storage I already mentioned. Again, these are just comparisons of heat release rate with time, with modeling experiments. One of the challenges that we face is lighter plastics. This is what we call uncartoned expanded plastic. Lighter plastics are making their way into everything. Things that used to be metal are now plastic. The lighter the plastic, the higher the fire risk. So this is what it looks like for a typical grocery store meat tray. That's the mesh. This is a high storage of that material, and this is a high storage of that material with one row of in-racks at 30 feet. Now, currently our standards say that to protect that, you have to, every 10 feet, put in a row of in-racks. Okay, so we're trying to see if we can push that limit and put larger sprinklers more strategically placed up at higher elevations to reduce the cost and burden for our clients. Here's the way we're using that to supplement, or the model to supplement tests. We have a simulation of the water flux to the bottom of the tier. This is the water that gets to the seat of the fire. It's not the density at the top, it's not the design density. And we have tests that we've done where we just release water in the same fashion to the bottom and measure it in the laboratory. So no fire test, just to make sure we have the water transport correct. That's really the root of the issue. If you get water to the right place at the right time, you're going to have effective protection. Okay, so in the spirit of, the test is reality, partially revealed. Okay, because you do a test, you only get so much data. A model is a lie, okay, because you're never going to represent everything, but it's fully revealed. You can dig in and find out what the problems are with your model by examining every variable in time and space. And we can use this information and then go back into the laboratory and do intermediate scale tests to find out how much water we have to deliver to the bottom of that storage for us to achieve effective protection. So we do intermediate scale tests where we have a well-controlled application of water to the top of the storage, not sprinkler control, but well-controlled application of water to the top. And we define the threshold where you have an insufficient or sufficient water flux. And the good news is in the bottom, you can see there's a lot of deviation between insufficient and sufficient. So that means you've got a big threshold, you've got a nice wide place to capture. The top is a little harder. And so with higher storage, it becomes a little more challenging. Nonetheless, we can use this. We go into the laboratory and test those scenarios. We've tested on both ends. And the ones that were predicted by this approach as being sufficient were indeed sufficient protection. The ones that were expected to be insufficient were insufficient protection. Okay. Now, what we haven't done, because these are expensive, time-consuming tests, is go back and see how close we can get to the margin. With safety factors in place, which there should always be safety factors, and this being an academic problem, I'm not sure it makes sense for us to do that, but we certainly would like to know what the uncertainty is around some of those margins as we move forward. Okay, so the benefits. Hopefully, what this kind of capability and this kind of approach and this strategy that we took, that everybody's a part of in the community, is reducing the number of large-scale tests for a specific problem. So with that in-rack storage application, rather than doing a minimum of 4 to 6 tests, we did 2. We did all the calculations. We understand the density at the bottom. We did one that we thought was going to be okay and one that we thought was not going to be okay. And we have something that we have a lot more confidence in. And of course, we can use that for maybe a little shorter, a little taller storage. We've used it to represent what happens if you pull a few pallet loads out. What happens if you have an open space? Is that better or worse? What happens if you increase the flue space or the aisle space? So ultimately, better, more reliable protection guidelines. Not reliability in the sense of the systematic reliability, but reliability in terms of we have information that will lead us to a protection point which we can put in our standards and ultimately get adopted, hopefully by others. Faster turnaround and support projects. We insure 1 to 3 of the Fortune 1000. Everything from amusement parks to semiconductor fabrication facilities. And they come up with some weird stuff. And so, we have a tool that we can use to address some of those problems. That's certainly a benefit. I think the most important thing, if we think about it, is hopefully we do have a platform now. And the partners that we've worked with so far in the university here can see some research value. We see, combustion and flame publications and things that are coming out, which is really the metric of success for universities and researchers. So we've seen that kind of come together. This is the slide that I always end with. When I talk to audiences about this, they say, well, are you just going to model everything from now on? Well, the answer is no, I don't think so. My tenure will not be as long nor as distinguished as John Doris's. But in my tenure, I don't think it's ever going to happen. It's certainly not, that's not the plan. I think the goal is to complement test data. Again, use the data as the truth partially revealed and the model as a lie fully revealed. There's certainly a lot of value in being able to do things smarter. This is the strategy we've taken. Hopefully, this group can see, well, you were a part of that strategy, and you can see now the ability to carry that strategy forward. Be part of the research team that's developing capabilities, putting it in the model, and be part of the group of users that downloads the model and uses it, and validates it for their application, because the model's never going to be validated. The model is the model. When you apply it to a problem, you validate it for your application. Validate it for their application and use it to meet their needs. So with that, hopefully I've left a couple minutes for questions.
Thanks very much, Lou. We do have time for a couple of questions.
Craig's got it.
Please do wait for a mic, if at all possible.
My guess is at this point, you're still doing 300 tests a year, probably learning more than you did before. Has it changed your instrumentation? I know you mentioned that you're conditioning your cardboard now, and that obviously an improvement. Have you changed other things in the way you do tests that came out of that?
Yeah, good question, Greg. And you're right. We've still got about a year backlog at the Large Bird Lab. We're still doing as many tests. So my commitment was never to reduce the number of tests in total. And it has changed some of the diagnostics. It hasn't made its way to the standard tests that we use to test and certify products like sprinklers. But certainly in terms of the tests that we do to develop new protection measures, we're starting to take more velocity measurements than we have in the past. Taking temperature measurements inside the commodity, so we can start to assess, the solid material response, and so it is pushing us to a better place experimentally as well. And then we've done some simple kind of global things about test quality as well. I mentioned moisture content. We kind of have a box of ambient temperature and moisture content around which we will do tests so that we can call them equivalent to each other. We've established that. And we have for our standard commodity, our corrugated material, we have like 27 parameters that we check to make sure that when we burn corrugated container board, it's the same corrugated container board that we burned last time. Because if you're using that for validation experiments, you need to reduce that you need to improve that repeatability. And what we found is that, in the past we had not necessarily done that well. And corrugated container board now, depending upon where it comes from, has more recycled content. That recycled content, shorter fibers, they burn a little differently than the virgin material that has longer fibers. So, yeah, it's driven a lot of quality improvements, and those, as I think was the spirit of your question, go hand in hand. It's not that you can go off and develop a model. Those two work together. So thank you.
Can I ask, have you used the technique at all in post-instant analysis, where there's actually been a fire in a warehouse to see what happened and what might have been done differently?
Yeah, that's a great question. We haven't done that yet. One of the challenges that we face with those situations is the fire service comes in and we're not quite sure what they did. In some cases, not sure they remember even what they did, because it's a hectic situation. So when they come in to do kind of the final extinguishment, it makes it more challenging. I think it's good insight on your part as we develop more confidence, as the use grows. You have cases where there was ineffective protection or cases where there was clearly effective protection. Something came on, a sprinkler controlled it well, the fire service came in and said, you're good, and didn't do anything. Those are going to be good test cases. Yeah.
Okay, I think in the interest of time, we'll move along.
Okay.
Thanks again.
Thank you.
Thanks very much.